Yeah. So any question from this time? This time we'll go over the midterm review. Okay. So now let's get backtrack to our algorithm algorithm course. So now we are ready to start to go into our first big algorithm, which is the shortest algorithm. So let's start with this small recap of the algorithm we talked about before midterm. So there was Deutsch algorithm, which solved whether f of 0 equal f of 1 with one quantum query. Then there's Deutsch-Josa, which we test on the midterm, and it tests whether your input is balanced or constant. And they also use one quantum query. Then there's Bernstein-Vazirani algorithm, finding this weird problem of the problem is f of x equal to s star x, and it basically runs on the same algorithm as Deutsch-Josa. And they also take one quantum query. Then there is Simon's algorithm, who do order and quantum query, and they can prove that classic algorithm you need to do 2 to the n over 2 queries because you are like finding collision. Then there is this famous short factoring algorithm, which give you an exponential speed up for this factoring problem. And we put the quotation mark here just because we don't have a rigorous upper bound for classical complexity, because there might be classical also very efficient algorithm. Practically, we know have this polynomial time quantum algorithm, and classically it seems to take exponential time, so it's an exponential speed up. Okay, so this is a very cool application. But before we go into very cool application, we need to talk more math. Okay. So yeah, we're going to talk about chapter 5 of the book. Let me change the color to green. Okay. Yeah. So this is our chapter 5 of the book, and it starts with the quantum Fourier transform, which is the center part of this shortest factoring algorithm. And just for a quick survey, how many of you have studied things about Fourier transform? Any kind of Fourier transform, raise your hand. No? Not really? Okay. So we need to go a little slower here. Okay. Yeah, and I guess if you take the signal processing course, we'll be all talking about Fourier transform. And if you are from EE, you should have about it. If you are CS, I guess it's elective. But anyway, so discrete Fourier transform. And the book talk about it in this weird way, but I think the easiest way to understand it of this discrete Fourier transform is it's a linear transformation from a complex vector of dimension to another complex vector of dimension. So what's a linear transformation is basically a matrix. So yeah, discrete Fourier transform is an n by n matrix, and it's a different matrix for different n. Okay, and so we just have it here. So yeah, here is the matrix. You know what's Fourier transform now. It's an n by n matrix where because they are going to be this complex size, so we say kj's element, matrix element, is 1 over square root n, and e to the 2 pi I, 2 pi, so those things are all multiplying together, so it's 2 pi I and times j times k over and divided by n. So it's nth root of 1, so the complex nth root of 1 times j times k. And the jk here is the kj here. Kj equals jk because the order doesn't matter, it's a symmetric matrix. Okay. And and so let's actually go to this example here. Okay. So here are some examples of the Fourier transform matrix. And for now, nothing is quantum. We are just talking about linear transformation. but you can probably guess that this is unitary, so we're going to apply this on quantum state. But for now, let's not think about quantum state or anything. We're just doing linear transformation on vectors. Okay. So yeah, so here are 3 Fourier transform matrix: F2, F3, F4. So basically, as small as possible. And you will see this one is quite familiar, right? So anyone want to answer what's this? Yeah. So this is a Hadamard matrix. Okay. So a lot of good property of Hadamard matrix is comes from it actually being a Fourier transform on a qubit, and so you can kind of see the matrix. So they all have a similar structure. So like the first row and first column are going to be O1, because when you count those JK, okay, so this is a bit weird. So when you count those JK, you actually count from 0. Okay, so yeah, because usually when we count index, we say like n-dimensional index, we count from 1 to n, right? And here the convention is actually you count this k from 0 to n minus 1, as you see here. Okay, so the first dimension is actually index 0. Okay, and otherwise you need to shift this around, but the convention is count from 0. So and which is j, which is k. So I think this is k. It doesn't really matter. So say this is k. So you can say that this column is k equal to 0. Then you see, I should write it here again. It's easier. So just for comparison, the elements are this overall vector of 1 over square root n. So 1 over square root 2, 1 over square root 3, 1 over square root 4 equal to e to the 2 pi I j k over n. Okay, and you see if k equals 0, then this thing is always 0. That's why you go a whole bunch of 1 here. And also j equals 0, then it's always going to be 0. And if it's not 0, then say k equals 1, and it goes through different j, then you have like the j equals 0 is still this 1, and j equals 1 is e to a 2 pi over 3, then you e to a 2 pi over 2, which is just e to a 2 pi over 3 squared, and etc. So that's F3, and F4 is similar, except the omega here actually becomes e to a 2 pi over 4, which is this I. And so you have this 1 and I times I equal to minus 1, I times minus 1 times I equal to minus I, etc. And you have this 1 and 1 and I squared and I fourth and I sixth, etc. So those are some examples of Fourier transform matrices. Any question? Question? Okay, no question. And okay, but for some reasons, the book and also following book our notation, we instead of just writing a vector equal to a matrix times another vector, we write in this Fourier transform way, because well, there are some interpretation of this Fourier transform. I should say there are some interpretation of this Fourier transform in its application in signal processing. So we are kind of thinking you have this vector is kind of signal, and we will transform it to another vector which has the same kind of info, this big F times X, and the Y vector has this component, and so we have two equivalent way of describing our Fourier transform. So obviously you can just write down its matrix elements, or you can also express in this weird way, which makes more sense if you think about signal processing. So you are thinking about what's the case component of Y, how do you express it as a linear combination of X. Okay. So you can check yourself that those two are the same expression because you can just multiply those on the x vector, and you will see the y vector, and you can see its component. And anyway, so the k's vector, so this k can be anything from 0 to n minus 1. And so this expression tells you how to calculate the k's component of the resulting transformed vector from all the amplitude of those x. And so the linear combination we need to multiply with this e to the 2 pi jk over n, and also 1 over the square root n. Okay? And people good with this notation? This is just this, but doing some basis multiplication. Okay. And then let's see some example of vector being transformed. So the first example is actually very important. And for now, we are not thinking about quantum state, so we just put whatever we can have whatever vector as input. And we can think of this as some classical signal, and it's a constant signal, it's 1, 1, 1, 1, 1. And so what happens when you transform this vector with the discrete Fourier transform, or you multiply with this matrix? And what happens is you will see the first component become 1 over square root n, and everything else becomes 0. It's a very high symmetry here. And how do we get this is this equation, which is actually very important. You need to remember it. So if you plug in this into the notation, you see that, okay, so this formula is actually easier to use now, right? Now you kind of see why we want to use this, because this directly tells you what the component are. So it tells you the k's component of the resulting vector is just 1 over square root n. Then the summation of these xj are all 1. So you are summing over a whole bunch of those e to the 2 pi jk over n, right? So these are the omega to some power. And when you sum over those things, and j sum over all the j from 0 to n minus 1, there is very high symmetry. So most of the time this is just 0. And actually, so this is 0 whenever k not equal to 0. Then, so let's say the singular case first. So k equal to 0, which corresponds to this dimension, right? When k equals to 0, well, obviously the exponent here is 0, so we are just summing a whole bunch of 1. And so this summation is n, and but you have another 1 over square root n. So this number is 1 over square root n. So that's easy. And when k not equal to 0, and we don't do rigorous proof here, but so we do this proof by picture. So like for example, k equal to 5, n equal to 5, and you think about your summing over all those points. And let's say k equal to 1, right? Say for now k equal to 1. Then what the points you are summing over? K equal to 1, so you just sum with j from 0 to n minus 1. So when j equal to 0, so this is a complex plane, so real axis, imaginary axis. And so this is a unit circle, right? And those points being the power of the roots of 1, they are going to be on those 5 points. So this point is e to the 2 pi I over 5. And let's say this is omega sub 5. And that's not rest up. So let's say this is omega. And so this is omega square, omega cube, and omega fourth. This is omega 5 equal to 1. Okay. And so when k equals to 1, and when we sum from j to 0 to 4, and so j equals 0 will be this point, and obviously j equals 1 will be this point, j equals 2 equal to this point, and 3 and 4. And those 5 points are equally spaced on this circle. So by some symmetry, or you can do series calculation, when you add together those 5 complex number, it will become 0 because they are equally spaced out on the circle. And you can feel that the same argument should go over any n. So any n those unequally spaced point on the circle, there will summation equal to 0. Okay. And we only go over k equal to 1. Right? And let's say if k equal to 2, we are also going to summing over those 5 points with just with different order. So k equal to 2 and j equal to 0 is still this point, and j equal to 1, then you will have 2 pi I times 2 over n. Okay? And j equal to 2, then we have 2 times 2 equals this. So we are going from here and here, and we over 2 slots every time, then we go 2 slots every time, and go over so 3, then we are here because it's 6 multiplied equal to 1, and then 8 multiplied equal to 3. Okay, so you see that j equal to 2, we go over like this weird star shape, right? And we are still counting over all those 5 points, and they still sum to 0. And so we don't give rigorous proof, but you can probably feel that. So you can do some number theory to convince yourself. But so for every k, when you sum over this j from 0 to n minus 1, you are just summing these 5 points for different order. Okay. So you are always going to sum over those equally spaced points on the circle, and they are always going to sum equal to 0. Okay. So that's the most important identity when you calculate this discrete Fourier transform. Okay, important. You need to remember this when you do things. Okay, so yeah, so we want k being integer and I equals 0 modern, and there are n minus 1 possibility, so that's why you get n minus 1 0 here. Okay, so this is for k equal to 1, k equal to 2, to k equal to n minus 1. Okay. Question on how this calculation goes. Okay. Let's erase a little bit of things here. Getting messy. Okay. So that's the Fourier cancellation, I guess. And here we have an easier example. So this example, we are picking up a single component on the input vector. Then the output component we will just read from here. So here xj only equal to 1 if j equal to 1. So j is only equal to 1, and you just read from this formula that it should be, well, the first one is always 1, then you have the omega squared, omega to n, where omega is this nth root of this nth root of 1. You can also kind of see this from the from the matrix notation, right? Because you are multiplying 0, 1 here, then you get this column, and you get 0, 1, 0 here, then you get this column, and you get this column. Okay? So those very Fourier columns. Okay? So that's some example of Fourier transform. And let's talk a little bit about interpretations and why do we want to write it in this way. Okay, so this is, well, not related to quantum algorithm, but something nice to know. So why is Fourier transform important? Because you will transform your signal between the time domain and the frequency domain. So the idea is that although I think the notation here is a bit weird, but let's suppose this is true. So, so the idea is that we want to do Okay, I'm not sure which direction is f, which direction is f minus 1, but suppose this is f. F minus 1. And so the idea is that we have some signal, let's say discrete signal, although we write a continuous line. So let's think about this maybe a discrete signal. So it's actually discrete sample points. But let's write continuous line so it's easier. So discrete signal and it has period big N, okay, like this. And let's say, and for period N signal, the most pure one is like a sinusoidal, a sine function, right? So think about sine function this. And so what we want to do with the Fourier transform is we want to pick out the frequency component of your signal. So we are thinking about breaking our signal into summation of different signs of different frequency. So let's say you have this constant function, then this thing has frequency 0, and so this function, so if your input is this constant function, and then you do, so this constant function on the time domain, and on frequency domain, it should tell you that this thing has frequency 0. And this is exactly what happened here, right? So we have this constant as input, and the output says that everything in the frequency domain is concentrated on this frequency being 0 component. Okay? And then if you have this frequency 1 function, right? This is the I guess except for 0 is the lowest frequency you can get for this period N. And then you do Fourier transform, it should tell you that you have frequency 1. And in terms of complex, is e to the 2 pi I j. Yeah. It's like xj equal to, I guess, omega 2j. But we are writing on sign because complex functions are hard to write. And anyway, so if you have this frequency 1, then you do Fourier transform, it should become frequency 1. And then you have this frequency 2, and then you do Fourier transform, it should become something concentrated on frequency 2. Should be a vector that will concentrate on this. And as we say, it should be e to the I theta. Right, so I remember. And as we said, we are drawing picture with sine, and maybe I should also draw cosine, but that's a little complicated. We are drawing with sine, but actually we are thinking about e to the I theta. And we think e to the I theta basically sine and cosine, so it's the same thing. And so let's not go into the detailed difference between being a complex exponential or real exponential. But anyway, so let's see what Fourier transform want to do. So if you are being a sinusoidal or complex exponential in the time domain, then you should become concentrated on the corresponding frequency in frequency domain. And what's interesting, but we didn't draw, is that, remember, this is a linear transformation. So now if you have the linear combination of some of these things, okay, now it's very hard to draw. So you have a linear combination, let's say a linear combination of those two on the time domain. So the signal kind of look like maybe this, I guess. And then, oh, probably not like this, right? You should look like this, maybe. Anyway, so you have a linear combination of this. Then on the frequency domain, you will also be a linear combination of those two frequencies. So you can read all the frequency components, and there are some completeness theorems that says that every reasonable function can actually be written as a linear combination of any kind of sinusoidal here, and That means you can always analyze your signal in terms of its frequency domain. I guess it's frequency domain signal. Yeah. So you can say is it higher in the high frequency or in a low frequency, etc., etc. Okay. So that's very interesting thing about signal analysis. You can study more in the DSP course. And okay, so first thing interesting thing is that it's linear, so you respect all the linear combination. And another interesting thing which you want to do in your homework is that it has a very simple inverse. So we talk about we can transform signal from time domain to frequency domain. Actually, this transformation doesn't lose you any signal. Sorry, doesn't lose you any information. And by that I mean you can actually do an inverse transform from frequency domain to time domain. Okay? So there is this on f-1. And they have a form that actually looks very like RF. So you need to prove this in your homework. F-1 has a matrix component equal to this. So you can see that this is a basic F, except that you have a minus sign here. Okay. So that's very cool. Okay. So that's Fourier transform. Any question? And if not, then let's get a big quantum. And okay, so how will we get quantum here? Well, it's a very obvious way. So now if we think vectors, so remember the vectors, those x and y. Now we think those vectors as quantum state, then we are doing quantum Fourier transform. Okay. I guess, okay, so it looks like this mathematically. And but we need to do different order. So the first thing we need to check is the quantum Fourier transform makes sense. Then this matrix, remember this matrix Fn, right? So we're basing upon this matrix Fn on our ket x to become a ket y. And for this to be quantum transform that makes sense, Fm need to be unitary. You need to preserve the norm of x. And so that's another thing you want to prove in your homework. So prove that this Fm matrix is actually a unitary matrix. Okay? So that's the first thing to check. But let's talk a little bit about idea under quantum Fourier transform. So as we said, so this discrete Fourier transform actually gets studied a lot before, and they use a lot in all kinds of engineering and science before people even think about quantum mechanics. So this is so discrete Fourier transform is something just very useful in all kinds of signal processing and things. And so the motivation of quantum Fourier transform is kind of different than what I set up. So the motivation is like we want to use the quantum state. So we want to use the quantum mechanics to do Fourier transform. Okay? Or yeah. So the idea is like Fourier transform is a good way to do analyze our signals. And the idea is in quantum computing is if we store our data in terms of some quantum state, then we can do quantum Fourier transform now as a unitary matrix on our state. Then if we can do this unitary very efficiently, then we can get some quantum speed up in doing Fourier transform. Okay? Yeah. So yeah, that's the idea. So we want to do this Fourier transform as a quantum state, and we'll see that we can actually implement it very efficiently, and the result is we can do quantum Fourier transform faster than classical Fourier transform in some sense, because there is a tricky point about storing your signal in terms of quantum state. But at a very high level, we are going to see that quantum Fourier transform can be implemented very efficiently, and thus arguably the root of the quantum speedup for the Shor's algorithm. Yeah. The speedup we get in the factoring algorithm is because quantum Fourier transform is faster than classical Fourier transform. Well, although there are some caveats. Okay, so that's the idea of one want to do quantum Fourier transform. But let's back to mathematics. And so as we said, discrete Fourier transform is, well, basically just quantum Fourier transform, except that you need to, first we need to make sure that this transform makes sense. This transform is actually unitary. And the second is we just change the notation to our familiar K notation, right? So remember we have this x vector, and it has this x0, x1, to xn minus 1 component. And if you write all that as our K notation, then all the bases, we just write this kj as computational basis, but now we count the computational basis from 0 to n minus 1, just because of convention. And you have amplitudes being those xj, and then this input vector, you apply your quantum Fourier transform, then you will become this output vector, which is, remember, is this y0, y1 to y minus 1. So you also have all the basis vectors. And well, the k and j are both non-evaluable, but just use different dummies for to make the to make the notation more clear. And anyway, so this k is also just computational basis from 0 to n minus 1, and you have amplitudes from being all those yk, and then yk is related to xj by this same formula. So this is just exactly same as what we had before. So yk equal to 1 over square root n, summation j from 0 to n minus 1, xj e to the 2 pi I over n times 0 jk. So your omega times jk. Okay. And so now there are multiple equivalent ways to write this, or you can think about the whole vector. So the whole vector y is just this Fourier transform matrix times your input vector x, and your and the jk's component of your matrix, as we say, should be e to the 2 pi times jk. Oh, sorry, no, we also made a mistake here, and divide by n. And there should be times 1 over square root n. Okay. Okay. So we have the matrix component, and or we can say, because everything is linear, we can also write this in I guess a more restricted form. So let's say we input with all the computational basis j. So basically we just have xj equal to 1 and all other xj equal to 0. And you put that in, and you will see your output vector. So then your yk will be 1 over n, and equal 2 pi j Kelvin, so the same thing, and then you can sum over k to get, remember the output vector is sum over k yk, so we are basically just combining those two expressions and see if you have a computational basis vector as an input, then output is this vector. And basically this is the whole column of this Fn matrix. Anyway, they are all very same thing in different expression. Okay, check it out the same. The important part is this exponential equal 2 pi jk over always going to be always here. Yeah. And so that's quantum Fourier transform is this unitary matrix. And now here we have a very general definition. So for every n-dimensional space, or n-dimensional, big n-dimensional quantum vector, you have one quantum Fourier transform. And it has matrix element like this. Any question? If not, then we don't have enough time to finish all this, but I guess let's start a little bit. We will start from here once again from here, but this is very complicated, so maybe it's a good idea to go over this twice. So we say that quantum Fourier transform can be implemented very efficiently. And yeah, so here we show how to efficiently implement the quantum Fourier transform. And this presentation is easier if we take big N as the power of 2. So it's 2 to the some small n. Okay, because this approach kind of recursively decompose your Fourier transform into smaller Fourier transform, but we won't see the structure too much here, so I guess let's go over the hard details. Okay, and so let's set up the notation first. And okay, so we will need to use this notation to convergence between number and the binary bit string. So this is just binary expression thing. Okay. Okay. So because we now have big N equal to the 2 to n, so we think big N is going to, so any number from 0 to big N, so any number from 0 to n minus 1 you are going to identify it with small n bit string, right? And this is how it works. So we think so, and that's basically just writing in binary. So we have some number j, then you can write in binary, then it's some j1, j2 to jn minus 1, and it means j1 times 2 to the minus 1 plus j2 times 2 to the minus 2 plus all the way to jn times 1. And you should be all very familiar with this. So your convergence between usual number and its binary expression. So for example, if small n equals to 3 and you have a 3n bit string, so this is 1, 1, 0, then it's 4 plus 2 plus 0, and it needs to equal to 6. So this is j1, j2, j3 equal to 6 equal to j. Okay. So just setting up this binary notation. Okay. And then we set up less conventional notation. So we also set up binary fractions. So we have 0.j1, j2 to jn, and anything after 0 point means that 1 over 2 to the some power. So it's j1 divided by 2 plus j2 divided by 4 plus all the way to jn divided by 2 to the n. And for example, 0.11 equal to 1 over 2 plus 1 over 4, and it's 3 over 4. Okay. And see, maybe, so we don't have time to go over details, so maybe it's good to see the starting, see the conclusions. And the conclusion is, if you want to do quantum Fourier transform, then you think well, it's linear, right? So basically you only need to think about what you do on computational basis state. And let's see. And what happens is you take a computational basis state, then you do quantum Fourier transform, then you will be seeing us doing these weird rotations on every qubit. So if you input with some computational basis state equal to j1, j2 to jn. So remember, this is doing this binary thing. And basically we are doing this interpretation. We are thinking what happens if you put in a computational basis state. Then your circuit should turn a computational basis state into this thing. So this is kind of like a whole bunch of Hedema, except you have this weird phase. Okay? So every qubit turn into summation between 0, 1, 0, 1, 0, 1. So you're kind of doing Hedema everything. But also you need to multiply every one with this weird phase. And so the phase is this e to the 2 pi 0.jn and e to the 2 pi 0.jn minus 1 jn. And so you keeps getting longer. And remember, this 0.jn is interpreted this way. That's why we talk about it here. So, for example, 0.jn. So if jn equal to 0, then this whole thing is 0, and the phase is just 1. And if jn equal to 1, then 0.1 in binary is actually 1 over 2. So this will give you a minus 1 phase here. And then if you have these things like 1/4 here, then you can actually give like I minus 1 or minus I or 1 here. So you have a different kind of phase from all those 0.jn or 0.j something. And anyway, so we'll see next time that this expression is true. So all these things actually equal to what we had before. So what we had before is so you see the 2 to the n over 2 is just 1 over square root n. So this is just what we had before. And you will see that this weird application of phase actually equal to our e to the 2 pi jk over 2 to the over big N, which is equal to 2 to the small n. Okay? And so this is what we will see next time. So for this time, we assume that this is true, and then let's jump over a little bit. Then we will see that uh, we will have this circuit as a circuit for quantum Fourier transform. So assuming your input and without loose generality, you can assume the input is computational basis, because if it's any other thing, then the linearity of quantum gates will just carry over. So if the input is computational basis J1, J2 to Jn, and then you get like this a bit weird Hedema and J2. Okay, sorry, we need this notation. And we have this notation of RK being this very small rotation of exponential 2 to the k 1/2 to the k dividing 2 pi angle rotation. Yeah, sorry. So anyway, so RK is this rotation of angle e to the 2 pi divide by 2 to the k. So you can see that when k goes big, then the exponential growth in this 2 to the k. So you are getting very small rotation, but that's exactly what you want, because you want, so for like n large, you get things like this 0 point something something Jn. So this is like so what I want to say is, you see the 0 e to the 2 pi e to the 2 pi times 0.00 dot 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 0 Jn is equal to e to the 2 pi I divided by 2 to the n times Jn, right? So this very fine angle is required to get this 0 point many bits of Jn here. And so what you want to do here is so you want to construct those qubits one by one. So you see this qubit has this weird, so it's 0 plus 1, so that's why you get this Hedema first. Then and then you want to, so if you do Hedema, then this become 0 and e to the 2 pi I 0 point J1 and 1, right? Because if, so let's do this a little slower. So if J1 equal to 0, then Hedema become plus state, so that's 0 plus 1. And J1 equal to 1, and you do Hedema, it becomes 0 plus minus 1, 1, right? And that's 0 plus e to the 2 pi I 0 point, okay, 2 pi divided by 2. So now remember we are in this weird binary notation. So that's 0.1, 1. Okay. And similarly, this thing is 0 plus e to the 2 pi I 0.01. Okay. So you see, if you do Hedema on J1, then you get 0 plus e to the 2 pi 0.J1, 1. Yeah. And then you want to add all the other bits together. Now you have 0.0J2, 0.00J3, and da 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 to 0.0000Jn. And that's why you do those control rotation from OR qubit. So from this J2, you do control the R2. So then you see that they exactly add up this bit. So when J2 equal to 1, you get this 0.0J2 here. When J2 equals 0, obviously you don't get any phase here. And similarly, every J give you extra phase here. So when you do all these gate, so AND gate here, you will turn the first qubit equal to this thing. And then similarly, you do on the second qubit and all the way up to the last qubit. Last qubit is the simplest one, so you turn the JN bit with a header mark, as we say. If you apply header mark on JN, it becomes 0 plus 0 e to the 2 by 0.JN1. Okay. So you do all those header mark in the control rotation, you will turn your state equal to this thing, and we'll prove that this is exactly equal to, well, we didn't prove that, but we'll prove next time that this is exactly what quantum Fourier transform should be. Okay. And yeah, there is a lot of math we need to go through, and we will go through it more carefully next time. Sorry for the overtime. Any question? Okay, so the most important thing today is you need to understand what's quantum Fourier transform. Basically, this matrix. Okay. Okay, so then let's see you on Thursday.
前面不是有写有看一个转换的关系是 J 的 exponential 的 I 这那个派 I 的东西。
这个吗？
对，就是我有个小问题是，所以说
它不是等于他说 J 转换到这个东西。
对，然后这边是指 depend on K， 就是所以说是 K 的变量，然后决定了 J 是多少。那我想
没有，这个不是 K 决定 J， 这是说，这个显得奇怪。这个是说，Fn J 会等于那个东西，会等于这个 1 over square root上 K e to the 2 pi jk over。
那这样的话，如果我可能，所以我那个 J 就是前面那个 basis。
这个是说，可能写成 matrix 比较简单吧，是我这个 Fn 的 matrix 嘛。然后 J 的话写成 vector， 就是说这里全部都是零，就在 J 的地方是1这样子。这里是 J 这个，对，然后说这个东西乘出来会等于这个东西，然后这个东西是什么呢？其实我也是把这个，其实我也是把一个 vector 写出来，就是 1 over square root 大家都有。然后第一个是会是。第一个会是1嘛，因为我们说一开始的东西都是1，原来是 k 等于0的时候它是1，然后 k 等于1的时候它会是什么东西？它会是2 pi I j 乘以1除以 n， 然后我们如果叫做比较简单一点 ，omega 等于1除了2 pi I 除以 k 除以 n 的话，那这个东西就会是 omega 除了 k， 抱歉 omega 除了 j。对吧？然后会是 omega 除了 2j， 大，一直到 omega 除了 -1j。对，所以这个 expression 就是要讲这件事情，就是要讲如果 Fn 达到这个 computational basis， 那它就会变成这样的一个 state。这个跟这个是一样的东西嘛？我只是把它写成。
好，是这样子。拜拜。